On a lab, David Kalmuk. He's a senior technical staff member who's been with the team for 14 years. Dave's implemented a number of features in LUW, most recently WLM support for BLU, but he's also implemented, he was on the original team for WLM in 10.1, did a lot of monitoring work in 9.7, and he continues working, leading the team with WLM for BLU processing going forward. So, welcome, Dave.
Okay, thanks, John. Everyone can hear me? I think the mic's on. Okay, so my session for you guys today is monitoring BLU acceleration in depth. I am going to try to take you a little deeper than the simple load and go, and go a little bit behind the scenes if you want to monitor and understand what BLU is doing. And what I'm going to try to cover for you guys today is sort of work across the board of different monitoring areas in BLU and give you some pointers on how you would approach monitoring the different areas that might be of interest in BLU and give you some examples on how to do that. So I'm going to cover a whole bunch of things. I'm going to do a very quick recap of the BLU technology for folks, just the general overview. I'm going to spend some time talking about selecting a workload and monitoring columnar query execution, so understanding whether your queries are getting the full benefit out of BLU. I'm going to talk a bit about monitoring columnar table size and compression rates, which is an important area because compression is a big draw or a big benefit of BLU. I'm going to talk a bit about the I/O, monitoring I/O for BLU, both Bufferpool I/O and Prefetch. I'm going to spend a little bit of time on monitoring BLU sort memory and performance, which is very critical in BLU. And finally, talk a little bit about the default workload management that we have for analytic workloads and how you can monitor that. So quite a number of things. So I'm going to move relatively quickly, but I have examples in each section, so they're hopefully there for you to come back and look at for any area of interest that you want to drill into further on your own. So let's get started. I'll do a very quick recap of the BLU technology. How many folks are pretty familiar with BLU already? Most. Okay, so I won't spend too much time on this. So BLU, of course, is our next generation columnar technology for analytics. There's really three key pillars to the technology in terms of the way we think about it. The first is, of course, query performance. BLU's columnar technology allows us to achieve order of magnitude acceleration for complex analytic queries. And if you've seen any of the other sessions, you've seen some of the data points. If you're using BLU for queries that are doing complex scans, joins, aggregations, you can get really heavy performance acceleration there. The second pillar of BLU is the storage savings. Because BLU is a column store, and data is basically packed column-wise onto pages instead of row-wise, you've got like values stored on the same page, which is very conducive to good compression. So you get very good compression with BLU, actually quite a good improvement over even our best adaptive compression for row. So that's kind of the second benefit of BLU, so the speed, the compression. And the third key benefit of BLU is just the simplicity. With BLU, we've really put forward this what we call load and go, which is a model where you can, if you set you follow our best practices and set workload analytics, create your database with that setup, we'll pre-configure everything for you. And then once you're actually running, because of the nature of the column store, there's a lot less setup. You really can basically load your data into tables, begin executing, and not spend all the time that you normally would spend tuning, creating indexes, doing these types of things. So that's kind of BLU in a nutshell. On this slide always turns black for me for some reason. But if you want to look at, BLU has a number of technologies in it, a lot of innovation from the IBM Research Lab. Just very quickly, a couple of the key things. So it is a column store, but it's kind of a special column store in the sense that it has what we call dynamic in-memory technology. So it is an in-memory processing engine, but we do not require that your entire data set fit in memory for BLU to work. So if your data set is bigger than the available buffer pool space, that's fine. We can accelerate, we can take a part of the data set, achieve the acceleration with that, and you don't actually need the entire data set to fit into memory. Other interesting things, I mean, my favorite probably is the actionable compression, the idea that when we pull data values into memory to process them, we don't need to decompress them to do the processing. And that's a very compelling piece of technology, because now you can imagine for a given cache line in the processor, we can fit that many more values in there and perform processing that much more efficiently. The memory efficiency of BLU is very good because of that. And of course, there's a bunch of other things. I mean, BLU is a highly parallel technology, leverages multiple processor cores. Even within those processor cores, vector instructions to really leverage parallelism on the system. There are other innovations in there like data skipping, where when we're doing range scans, we will skip entire ranges that we don't need in queries. So a whole bunch of very good innovations in the technology. And that's really how it achieves those key benefits, like the accelerated performance, the compression. So don't want to dwell on that too much, but I wanted to do a mandatory introduction. Let's get into some of the monitoring topics. So I'm going to approach this kind of stepwise and work through each area. First area I want to talk about is how to select a workload. And once you've selected a workload, a few of the things you can do with the DB2 server in terms of monitoring query execution to understand what's going on and how much you're actually able to benefit from BLU. So in a nutshell, I could really sum up this slide in one point, which is BLU is really aimed at analytics. It's aimed at complex queries that do a lot of data crunching, do heavy scans. It's not aimed at OLTP. It's not aimed at very simple point queries where you're doing single record lookups. So those are the types of workloads where you're going to see the most benefit from BLU. So these would be things, analytical workloads, data marts, the types of processing, processing very large data sets, grouping, aggregation, range scan, joins, complex queries. Also some benefit for queries that have a lower column selectivity, so only touch a small number of columns in large tables. And these are typically star snowflake schema designs. Also, we have BLU integration with SAP Business Warehouse. So those are the kind of workloads you're going to want to aim BLU at. OLTP is just, the columnar technology is not really designed for OLTP. There isn't enough work done in, OLTP, if you're doing index-based record lookups, you get a single row, you update the row, you put it back. You can't get much faster than that. So that's the general message. Now, I'm not going to be talking about the tooling in this presentation, but I do want to quickly mention the Optim Query Tuner, because it has an advisor that you can use that will identify candidate tables for conversion to columnar format. So it analyzes your SQL workload and can make recommendations for you on which tables you want to convert for BLU. So under the covers, I'm going to talk a little bit about some of the monitoring metrics we added to facilitate this type of analysis. The first are metrics that we added related to column selectivity. So again, this is a way to determine if I have queries hitting tables, how many columns are these queries actually selecting on the table. So there are two metrics, and I've got an example here which shows them. The first one is called section executions with column references. It's a really fancy way to sort of say how many queries hit the table. And then the other one is the number of columns referenced, which is the total count of the number of columns that each query has referenced. So if you execute 2 queries against the table and each of them query 2 columns, that total count would be 4. And of course, the section executions would be 2. So in my little example here, we picked out my schema, my table. We pulled out these metrics, and what we're seeing in my example is that we had 655 queries that actually reference this table, and on average, only 2 columns were referenced per query execution. So you can imagine if this table, for example, had hundreds of columns, this would be an indicator that you could gain an awful lot of efficiency with a columnar format, even ignoring the need to do joins or complex operations, because we wouldn't actually need to read those other columns that you're not selecting. There we go. So another thing we have for monitoring general columnar query execution. So you may or may not be familiar with our time spent metrics. This is a concept we introduced starting in 9.7. The idea is to provide a hierarchical breakdown of where your time in the server is spent. So when you're looking at something from either, if you're looking at your whole database, it's kind of a breakdown of where all the request processing in the database since the database was activated has occurred. At the query level, it's breaking down specifically during query plan execution where your time was spent. And what we've added specifically for BLU is a new time spent element which tells us how much time we actually spent in the columnar runtime. So if you think about, if you imagine a query executing, think of something simple like a select star. If you execute that on a columnar table, the BLU engine, the optimized BLU engine, is going to be reading in that columnar data. But at a certain point, so I mean select star isn't really doing much processing, we're just scanning the table. To return that data to the client, we're going to need to convert it into the standard row format. So I guess what you want to think about is that every query is going to have some small amount of processing in the conventional row engine, even if it's only to convert the final result from columnar to row format. But you're going to have a subset of time spent in the columnar engine. And with these times, what you can basically do, you can take our total section time, which is the total plan execution time for your query plan, and then you can take the total columnar time and see what percentage of the query processing time was actually spent in BLU. And for maximum benefit, you're going to want to see this number be quite high. In this example I had, the number was 80%, which is not bad, could do better. But the idea is this is a very quick indicator to tell you if the query you're executing is really leveraging the columnar runtime and getting the acceleration. If there are certain constructs in your plan that can't be pushed down into BLU, so if you run your query, you check this time and it's a very low percentage, that's an indication immediately that you're not really getting the benefits out of BLU. You may want to dig in a little deeper to see what's going on in your query to understand why you're not executing in the BLU engine. And I've seen this on occasion where you look at a query and say, it's just, why is it not getting the acceleration you want? And you look at it and you realize that a chunk of the query is not executing in the BLU engine, and that's the problem. So tying into that are explain and runtime explain facilities. So basically our most granular level of diagnostics for query performance analysis, where you actually look at the plan, and we have some nifty things like section actuals and object metrics if you do a runtime explain and actually capture the SQL. But the key thing from a BLU perspective with the explains is this CTQ operator. And this operator really denotes the boundary between the row and the column-oriented processing. So where that is in the plan is a very good indicator to help you understand how efficiently the plan is executing and how much benefit you're getting, or how much you're leveraging the BLU, the columnar runtime. So a couple of things to look at: position of the CTQ in the plan. Cardinalities are also useful to understand how much data is actually flowing out of BLU and potentially how much processing is being done in the row store. And what you're really looking for when you look at the position of the CTQ in the plan is what query constructs are in the plan, because there are certain things that BLU can't push down. For example, today, sort, OLAP functions, non-equality joins can't be executed natively in the columnar engine. So if you have these constructs in your plans and you're seeing things aren't being pushed down to BLU as much as you thought, that would be the train of thought to figure out what's going on. So just a very simple example. Here's an example of a query that we characterize as relatively optimal from a columnar processing perspective. So we've got a query with a couple of joins, some aggregation, and some ordering at the end. And what you see here, if you look at your query plan, the CTQ is right at the top. It's right under the sort. So your joins, your grouping, all your scans are happening within the columnar engine. The only thing we're popping out to do in the conventional row engine is the sort, because the sort can't be pushed down into BLU today. So if you see a plan like this, chances are that you're getting pretty optimal execution, because the vast majority of the query processing is in BLU. Contrast this with a plan like this, where the CTQs are actually sitting right on top of the table scans. So in a nutshell, what's happening here is the columnar engine is scanning the columnar data and we're immediately converting it to row format and then performing the bulk of the query processing in the conventional row engine. And in this case, obviously, you're not going to see the acceleration benefits of BLU because we're not actually in BLU. Yes?
A question on the limitation for the sort. Is this true for all kinds of sort, or can the binary collation be pushed down into the column engine?
I believe it's all kinds of sort, but I would have to check that to be certain. So we can follow up afterwards, I'll make sure. So I guess the key point in this plan, if you're wondering why things aren't pushed down into BLU, it's the non-equality join here, where we're doing f dot client dimension key greater than c dot client dimension key. We need to use a nested loop join for that, and today, at least at this exact moment, nested loop join, we don't have a nested loop join in BLU, only hash join. So that's why you see this plan. So again, easy ways that you can look at when you're looking at query performance and plan. In query performance in BLU, easy things you can look at to quickly determine whether things are executing normally. Without needing to go too deep, you can learn a lot from these types of techniques. Okay, so moving on to the next section, of course, compression is a key benefit of BLU. So one of the things you're definitely going to want to be able to do is monitor your columnar table size and compression rates. I've got a couple of things for you here. First thing is monitoring the columnar table size. So this can be done through our admin get tab info function. That would kind of be our baseline. Other functions like mon get table also work. The thing I would want to tell you about monitoring table size in BLU, there's really 3 areas you need to care about. So we have, if you're familiar with the way we lay out our storage objects, we have a couple of different storage areas in our physical storage. So you may be familiar with the data area where we store our normal row-based pages, indexed object area where we store index-related pages. For columnar storage, we actually have a separate area where we store columnar pages. So this would be the columnar user data, your actual pure data pages. So if you want to know the size of a columnar table, you've got to add up these 3 areas. And in BLU, what they are, so the columnar object physical size is basically your raw columnar data. We do have some metadata in the conventional row data area, and the main metadata in there is actually your table dictionaries. And finally, we do actually have some index-related storage in BLU. These are mainly 2 things, the page map index that we use to resolve individual pages from ranges, and also if, especially in Cancun, if you're applying unique key constraints or primary key constraints, we have an index under the covers to enforce those, and those would be taking space in the index area. So if you want to query the size of a BLU table, you basically can add these up. Simple example here. So if you're trying to compare space usage in a columnar versus row table, same table just in the 2 different formats. For BLU, you would want to make sure you look at the columnar data and index size. For the row table storage, you would only need to look at the data and index size. Although technically, you could use that first query for both. The columnar size is just going to be 0 for the row tables. So a very simple way to look at the size, the actual physical size of your columnar versus row tables. Another key point, generally if you want to do normalize to do as much of an apples to apples comparison as you can, you're going to want to include any MQTs that you've created for your row-based tables as well, because with BLU we don't need the MQTs. So this would be a storage savings that otherwise wouldn't show up in your comparison if you don't include them. So moving on, next thing, so we talked about storage size, but of course storage size is post-compression. So one thing you may want to know is what the actual compression rate is for your columnar table. We can do that fairly easily. The recommended method to do that is to look at the % pages saved column in syscot.tables. So when we collect statistics, we will compute this % pages saved. I've got an example here in the middle where I'm showing so if in syscat.tables, if you look at table schema, table name, and % pages saved, you can see for each table in your system what the compression rate is. And if you flip this around with this equation, what you can do is you can plug that in and also get the compression rate. So a 90% pages saved is basically 10 times compression. Couple of other key points. There are a number of compression statistics we have for row compression that don't apply to BLU because they're based on actual row metrics. For example, average compressed row size, average row compression ratio, percent row compressed, average row size. These are all based on row-oriented compression, and of course with columnar we compress column-wise, not row-wise. So those don't apply. Another key point is that admin get tab compress info is currently not supported for columnar tables, so that's why we point you at this metric to assess your compression rates for BLU. Okay, final thing I want to talk about in terms of storage and compression. Another thing you may want to do is actually look at your table dictionary quality. So even with knowing the storage size and the compression rates, another question that's important to ask is, am I seeing the optimal rate of compression that I can achieve? And we have a metric, or we have a column in our syscat.columns table in the catalogs called percent encoded, which can help with this question. So what this value is for each column in each table on the system, we have a metric which tells us how many of the values in that column were actually able to be mapped to an encoded, a smaller compressed value. And that's what this percent encoded is telling you. So if you're looking at this value, if you see something like we have on the left here, where your percent encoded for columns is 90%, 75%, 100%, that's an indication your dictionary quality is pretty good. You're probably getting near optimal compression. And as long as you're also seeing a good compression rate and good storage size, you're probably good to go. If you see something like what you're seeing on the right here, where your numbers are very poor, either 0% or 10% compression, that's an indication that something's gone wrong with the table creation. You've got a poor quality dictionary. And this is going to potentially hurt not only your storage space, but also query performance, because with BLU, of course, we can keep those values compressed when we process. If you're getting poor compression, that means that each individual value in the table is bigger. It's going to take more memory bandwidth to process. You're not going to be as efficient. And usually, the reasons this would occur would be things like your initial load was done with a very small set of data, so we weren't able to actually build a valid dictionary. If your utility heap was severely constrained, if you didn't use the default load and go for BLU, if your utility heap was very constrained, we might have had to drop or simplify our histograms when we were building the dictionary. In general, the message is if you see this, you're going to want to go and revisit and potentially reload the data in your table, because these dictionaries are set once the tables are loaded, and you're not going to want to run with this sort of compression problems. I guess two other interesting points that have come up in past discussions on compression for BLU. In terms of the toughest things to compress, these would be large, as you might expect, large character data, which can be highly random, much harder to build suitable compression for just by its nature. We have made improvements in Cancun for encoding character data, and it's in an area we continue to look at. Because it's probably one of the toughest technical problems is how you take large, highly random strings and achieve a good level of compression with them. A common misconception is that if you have primary key values in BLU integer keys, for example, that have high uniqueness, don't have many duplicate values, that we're going to get poor compression for those, and that's actually not the case. The reason is that although the majority of our compression is frequency compression using Huffman codes, where you see values that repeat many times and come up with a very small representation for it. We have other types of compression that we can use in BLU, including something called offset compression, where we will basically store a base value and then just store the smaller offsets for values that are near that base value in a particular range. And that works very well for things like unique integer keys. So we can actually get quite good compression on those, even though they're relatively unique. Okay. Yes?
David, what about compression of big int? Because big int has problems usually with index compression. But what about the general compression configuration in BLU for big int.
I'm not aware of any specific problems with big int. I can check that to be certain, but I'm pretty sure big int compresses just as well as integer.
Okay. Just going back a bit to where you were calculating the table size. Does the synopsis table get included in those figures?
To include the synopsis, so on the synopsis, that's a good point, good question. The synopsis table was not included in the example I gave. You would want to pull the admin get tab info for the synopsis separately and add it in. The synopsis table, actually, the footprint tends to be quite small, though. It's about 1,000th the size of your original table. So it's typically not a big impact on the overall numbers percentage-wise. But if you want to be 100% accurate, you would want to include those tables in there, too. Okay, talk a bit about Bufferpool and I/O performance. So of course, a big part of the in-memory efficiency for BLU comes by having a lot of compressed data in the buffer pool ready for access without needing to hit disk. I would say it's unimportant element in the achieving maximum performance with BLU. I would say it's not the #1 element. In my experience, at least, the actual sort memory configuration and avoiding spilling is the #1 thing that affects BLU performance, besides, at least at a system level. I mean, beyond actually looking at query plans and rejigging your queries to be more efficient. In terms of system performance, I'd rate sort memory as #1, buffer pool as #2. But of course, you're going to want to make sure that you have a decent sized buffer pool and that you're getting an efficient hit ratio. Since, as I mentioned, the column-oriented pages are in a separate storage area from row-oriented pages, we've got a set of new monitoring metrics in the buffer pool for monitoring physical and logical reads. So it's basically a columnar metrics for all the standard buffer pool metrics you'd be used to. So logical reads, physical reads, pages found in the local buffer pool, writes, all the async variants that tell you when we're doing prefetched columnar activity. And these metrics are available in all the standard monitoring interfaces. So anywhere you'd normally pick up buffer pool metrics, we now have the columnar counts as well. So a very simple example here. So when you're looking at buffer pool performance for BLU, what you want to do, you want to make sure your buffer pool size is within the ranges recommended by the best practice, which is for a single database system would be 25 to 40% of system memory, depending on how much concurrency you're trying to hit the system with. You can check your buffer pool heat ratios, make sure they look reasonable compared to your actual configuration and data size. So that if, this is mainly a precautionary thing. If you're following the load and go, you're using workload analytics, we will configure the system appropriately. But if you come into things from a different angle where you're doing more manual configuration, the hit ratio would just be an indicator that says, I better check my buffer pool size. And then, of course, the actual hit rate you get would be based on your active data size compared to how much memory you have on the system and how big you can make the buffer pools. Another interesting thing when monitoring buffer pool performance is to look at your temp I/O activity. So if you see a lot of temporary columnar reads, that would be an indication that we're spilling during query processing, and an indication to look at your sort memory configuration, because that can have a big impact on performance. Just an example here for you guys. Nothing really terribly groundbreaking here. Is just pulling out standard hit ratios from the buffer pool, but including columnar data. So here, in this example, I just pulled the row page hit ratio, the column page hit ratio, just to show how they can be obtained separately, and the total page hit ratio at the database level. Okay, so second area in terms of I/O performance that you're going to want to look at for BLU would actually be our Prefetcher performance. So BLU relies heavily on prefetching, and we have several metrics that we've introduced for columnar data, analogous to existing Prefetcher metrics that you can use to keep track of the efficiency of the Prefetcher subsystem. So again, it's basically the number of physical reads total, the number of physical reads done by the prefetchers. We have a couple of other metrics. This skipped prefetched unit of work columnar physical reads. It's a fancy way of saying how many times did the prefetcher go to fetch a page and it was already there. And the reason that would happen is if the prefetchers are somehow not keeping up and your actual agent worker thread executing the query needed the page and had to actually fetch it synchronously from disk himself because it wasn't there. So that's a good indication when the prefetchers aren't keeping up and something is bogging down that subsystem. Prefetch wait time is a bit of a special metric. That measures the time that your query spends waiting when there's a collision on the page. So that would be where the prefetcher is not keeping up. And when your agent thread actually goes to fetch the page, he collides with the prefetcher and needs to wait for it to finish executing the page. So that's kind of the middle ground of when we're almost keeping up but not quite. So what you're going to want to look for when you're monitoring this data, for scan-heavy workloads, we expect the prefetch ratio should actually be close to 100%. So that's a key indicator. Of course, those skip prefetch pages, if we're not keeping up, you're going to start to see that value increment up. And the prefetch wait time will catch the cases where we collide in between. So if you're seeing a lot of that, if you're seeing indications that your prefetchers aren't keeping up with the workload, a couple of things you're going to want to do. First would be to check the configuration. We recommend automatic. We'll actually then compute based on your system hardware the appropriate parallelism for prefetchers to make sure that we can perform well. And this would be the setting if you followed the load and go best practice for BLU. Another possible reason, if everything looks, the prefetcher subsystem looks like it's properly configured and you're still seeing problems, this may be when you want to start to dig into storage. Because if we are seeing efficiency problems in storage, if it's taking longer to do IOs than we expect, that will bog down the prefetchers and may cause us to incur these misses. So simple example here. I just extracted the metrics we talked about from at the database level. In my case, this was for a short workload where we write about 3 million pages. Got a columnar prefetch ratio of 99%, so very good, no indications of problems. No prefetch wait time whatsoever, and only a single page that we had to fetch ourselves because the prefetchers didn't have it in time. So something like this means everything's running pretty healthy, no worries. Yes?
A slide or two ago you said that column-based pages are stored separate from the row-based pages in the Bufferpool. What's the dividing line? That sounds a little bit like non-block pages where a section of Bufferpool memory is set aside for special purpose. Is it 50-50 split? What's the... It's not quite like that. We don't actually, there's not a fixed size in the buffer pool that's reserved for columnar pages. It's just that on disk, it's a separate area. So from a buffer pool perspective, it's really, there isn't that differentiation, if I'm making sense. So they cohabitate?
They cohabitate. They cohabitate. Very much how data and index pages cohabitate today. Columnar data and index pages can cohabitate in the buffer pool. So it's more how we put it on disk, and the reason we had the separate hit ratios is because we anticipated that perhaps because the columnar access patterns are different, it might be useful to be able to split out the columnar hit ratio versus the row hit ratio. But otherwise, it's not like block pages where you actually have a small piece of the buffer pool carved out.
Thank you.
Okay, no problem. Okay, let's see how we're doing on time.
Question?
Yes?
Is there no way to see the effectiveness of data skipping?
I do not have that in this presentation. I'm going to think about that for the moment because I didn't come in ready to talk about that. I think probably better, I'll take that offline with you. I'll look into it. I don't have any immediate examples for that. So I'm not sure off the top of my head if we have a very good way. I seem to recall looking into it, and we didn't have a immediate, simple way to tell you that, but there may be something we can do.
The related question, is there a way to see the space reclaimed? So how much space is used by deleted rows, which is not yet reclaimed?
I believe there is. I'd have to check into exactly how to do that. Okay, so a couple of follow-up things like I can chase with you guys afterwards. I believe I had two, if I'm remembering where we are, two more areas to cover. BLU sort memory consumption and performance. So this is a very critical area for BLU performance. Just to back up and give you the background. So the BLU, this is a very simplified version of the BLU Memory Model. What I really wanted to make sure was clear before I start stepping into the monitoring is how we configure sort memory in DB2. So for BLU, you can only use our newer shared sort model. That's because we use intra-query parallelism. So you can't use private sorts for BLU, so I'm going to talk purely about the shared sort and shared sort monitoring. Two parameters that we have on the database that allow you to configure sort memory. S-heap thresh share is basically the total available memory you're setting aside for sorts on the database across all queries. And sort heap is a limit on the amount of sort memory we will give for a single operator in a plan. So this would be things like group bys, joins, vector buffering. And the message, I guess, sort memory is a little bit of a misnomer because this is used for much more than sort. What we call sort memory really would be more appropriately called working memory in DB2. So this would be the memory we use for things like building up buckets of aggregations for group by, actually building the in-memory hash table for a hash join and that we do the probing into. We allocate that out of sort memory. So where Bufferpool is the caching of physical data pages in memory, the sort memory is the working memory that we use to actually compute and do the heavy lifting in BLU. So obviously, having sufficient sort memory is critical for your query performance. And in my little example here, I'm just trying to show that in this plan snippet, where we have a hash join, a group by, and also the columnar table queue itself will also buffer data, so it uses sort memory. Each of these would be considered a sort consumer, and each of these would potentially be allowed to consume up to sort heap worth of memory. So even just by peeking at the plan like this, you immediately have a view on the absolute high watermark for how much memory it could consume. Although typically a query will not consume, the operators will not consume the entire sort heap. So what we want to look for in terms of sort memory when we're monitoring it, first thing we want to do is make sure that the sort memory configuration is within the best practice range. For sort memory, that's about 40 to 50% of system memory, or 40 to 50% of the memory you've devoted to your database. Sort heap, we recommend a ratio of either between 1 to 5 and 1 to 20 of S-heap thresh shared. The exact setting depends on concurrency. 1 to 20 is more of a good baseline setting because that'll configure you to handle higher concurrency on your system. Again, if you follow the best practices for BLU, we will pre-configure this for you, so you won't need to touch it. But the reason I bring it up is there's certain situations where it becomes relevant. One thing you would, where we would care, if you're running on a highly constrained system, for example, the minimum recommended memory for BLU is 64 gigabytes. If you're running with that minimum, you may want to pay a little more attention to these parameters because configuring, if you're running on a system like that, relatively low concurrency, you might want to actually do a little bit of tuning, increase the sort heap a bit, give it a little bit more room for queries to run. If you're running on a well-provisioned system with 128 gigabytes of memory or more, where the constraints are not as much of a concern, the out-of-the-box defaults should be fine, and you most likely will not need to touch them. But here I'm trying to give you that deeper level view of if you actually want to know what's going on under the covers. So what can go wrong with the sort configuration? Well, there's really two things that you're trying to be on the lookout for. The first is to make sure that your workload has not exhausted the available sort memory on the database. If that actually happens, what's going to happen is then queries won't be able to get the memory they need. They'll start needing to spill temporary results to disk in order to process. And because we've exhausted the overall memory on the system, what it's going to mean is that you're going to get very unpredictable results. It's no longer that a certain query is so big that it has to do a bit of spilling. A query might unexpectedly get denied memory even when it's trying to allocate just some small minimum. So you're going to get spilling, but not only spilling. In the worst case, we can actually have query failures if we've exhausted the sort memory, if queries can't get their minimum amount of needed memory to run. So definitely you want to make sure that this doesn't happen. The other reason we may cause spilling and see inefficiencies is just if our per operator limit is not big enough for certain queries. Very large complex queries may need to may need more memory than that for particular operators, in which case we'd have to spill, and that will slow things down. But again, on a healthy size system, typically the spilling would only occur for the absolutely most complex plans, and in those cases, you're likely in a case where we're going to need to spill anyway. At a certain point, there's certain queries that are so big that we do need to do the temping of data in order to execute them. But if you're seeing these types of things happen, what you want to look at is three things. You want to look at the total memory on your database, potentially whether that can be increased if you're seeing memory constraints. The sort heap ratio is something you can tune as well. And you would normally do that in conjunction with the default workload management. So your options are basically, if the sort memory is underutilized, you can potentially increase the per operator limit and or let more queries into the system at a time. If you're finding that the sort memory is highly constrained, you can choose to reduce the per operator limit at the risk of causing more spilling. An alternative way to go about this is actually to reduce the number of queries we're letting into the system at a time, so that your queries can spread out and run. And we just manage things by being a little more sparing in how many things we let compete for the resources at the same time. So let me just quickly walk you through the metrics we have for monitoring sort in BLU. So first thing, sort memory usage itself. There's really depending on how you look at, 2 or 3 metrics. So we have a sort share heap allocated, which is kind of your point in time, how much sort memory am I using on my database. We also have a top metric, which is the high watermark, which tends to be more interesting because that's your peak. We also have what we call a sort consumer share heap top, which is new in Cancun, and that is really telling you the high watermark for your single largest sort operator in a plan. And these metrics are available at many levels of reporting now. So prior to Cancun, we could only get these metrics in aggregate at the database level. As of 10.5 Cancun, we've expanded this to basically be surfaced by all our core monitoring interfaces. So you can go, for example, to the package cache level and look at the sort memory consumption per query. And that's very useful in BLU because that can help you assess what the footprint of your queries are and in essence, how many queries you can reasonably let into the system at a time. So here, a very simple example at the bottom, just showing the current sort memory and high watermark sort memory at the database level. Second type of metric we have for you is sort consumers. So really, these are counts of the individual operators in a plan. As you see here, these are the major ones. There are actually more esoteric metrics, but the key ones of interest are typically hash group bys, which are columnar group bys, hash joins, OLAP functions, sorts. In Cancun, we also introduced a count for columnar vector consumers, which is just us buffering columnar data and passing it through operators in BLU. Now, why these are interesting and what you want to do with these, they tell you the number of operators we've executed in the plan. They also tell you a corresponding number of how many of these operators actually overflowed, which means spilled, and or were throttled. So the post-threshold counts indicate when we may have granted less memory than was requested, although we didn't spill because of memory constraints. So by comparing these two numbers, you get a quick idea for how many of your operators are actually executing fully in memory and how many are actually needing to spill to disk. And if the percentage is high, that's an indication you might want to look at your sort configuration. Second set of counts. I think I'm going to 12, John. Started at 11. So sort consumers. This is a slightly different way to look at it. So you've got these counts. You should say, what's this difference between this total and the active count? So the very simplest way to explain this would be the total is just the total count of operators that executed for the whole query. So if I had a query where I did, an imaginary query construct where I did a hash join, followed by a hash join, followed by a hash join, and somehow we executed those in sequence, not in parallel, the total count would say 10 hash joins. The active count would only say 1. So the active count is actually the number of concurrent operators that we're seeing. And the reason we have a separate set of counts is because you may want to, when you're looking at the memory footprint for your query, not just know the total, but actually know what the high water mark was for the total number of parallel operators. So the most useful way to do that, the active sort consumers metric that I have at the top here, is actually the sum of all the different sort operators. And by looking at that, you can immediately see, this query, although it had many, many operators, at most it was executing 5 at a time. And I can make some conclusions based on that. These, of course, are also available in all the same interfaces that we report our other metrics in. Okay, a couple of examples for you here just to illustrate some of the things I was talking about. So first one, simply looking at the database level and grabbing some metrics that help me assess whether I'm spilling and whether I'm memory constrained in sort. So what I'm doing here, I'm going to grab the total count of some of my key operators, sorts, hash joins, hash group bys, as well as the overflow counts so that I can compare the percentage of operators that spilled. And the other thing I'm pulling out here is the sort share heap top of the database level. So even with this simple query, I can do two things. The first is I can look at the high water mark and check to make sure it's not too close to my configured S-heap thresh shared. If it's hitting that boundary, it means that I'm exhausting sort memory on my system, and I'm going to need to take some action because that's going to cause spilling or unpredictable behavior. If that level looks okay, if my sort heap top, I have room to grow, I'm not all the way at my sort heap, S-heap thresh shared configured level, and I'm still seeing spilling, then that's telling me that my operator level sort memory, there are certain queries that can't fit in that size and are needing to spill. And depending on your workload, you can look at the percentage of operators that have spilled and make a determination on whether any tuning is in order. In my personal experience, and I won't claim to have, I'm not a field person, so I have some limited customer engagement, so I won't claim to know everything about BLU, but in my personal experience, seeing something like 25% is on the high end. Typically we can get, from what I've seen in engagements I've been involved in, we can get a lot of queries running without any spilling, and there's usually a handful of very big ones that are going to need to spill. But if I saw 25% on the system for BLU, I would want to go in and dig a little deeper to understand what was going on. Final query for sort memory or sort usage that I have for you guys. This is actually going now to the query level. So querying mon get package cache statement, which gives me aggregate information for all the SQL statements in my package cache. And here I'm going to extract a bunch of information, including the actual total sort usage for the query, the biggest individual sort consumer in that query, and the total number of concurrently active sort consumers. I'm also going to pull out the counts as before for the total number of sort operators and the overflows, as well as the number of throttled sorts. So pulling out this type of information gives me a ton of useful stuff. It allows me to figure out by query which ones are actually spilling, and even more granular, which operators are spilling. So if you go into the actual query plan, you can get a sense for, you look at the cardinalities, you get a sense for why we might be spilling. Total memory usage I find extremely useful when looking at queries, because that's probably the single most important metric, because now I can sort of say, okay, my sort size is X, my queries are consuming Y memory, I can fit 5 of these in the system at a time, or 10. If I increase sort heap and I monitor these things, I get a sense for the dynamics of how my system should actually work, and what's going to work and what isn't. Okay, so final thing I want to talk about is the default workload management for analytic workloads, because it obviously, as you might assume, or you might gather, it's a key point of how you tweak your memory. If we give more memory per query, we can fit less queries in the system at a time. Conversely, if we want to fit more queries in the system, we give them less memory. So I want to just touch on this very briefly and show you a couple of queries for how you would monitor the default workload management. So just to back up and explain what this is all about, as you may well know, part of the BLU philosophy, how BLU achieves its acceleration, is that it tries to leverage the full machine resources. Highly parallel, leverages all CPU cores, tries to buffer as much data in memory as possible to achieve maximum acceleration. But bottom line is this means BLU queries are pretty heavyweight beasts when they're in your system. And if you try to run too many of these at once, you can get significant resource competition, which can degrade your performance. So, and in the worst case, if you've got too many queries running in your system at a time, you can exhaust resources and potentially cause query failures. So we knew coming into 10.5 GA when we were going to ship BLU that we couldn't just go out the door without some sort of query concurrency management built in. So as part of our workload analytics, we added a default workload management configuration with the goal of externally allowing effectively an unlimited level of query concurrency, but internally managing the number of queries we'd actually execute at a time to ensure that we would not overload the system and that you wouldn't need to worry about this when you were running concurrent workloads. So just a very quick overview of what the default workload management looks like. It's a rather simplistic model, but it's quite effective for moderate concurrency. So whether you knew it or not, since 9.5, whether you configured workload management or not, you were actually running with the default workload management configuration. And it was a very simple configuration where all your user requests would be mapped to a single user service class and run in a default subclass in that service class. No controls whatsoever. But if you looked at the monitoring, you would see that there's work running in that service class. In 9.5, what we did is we split that default subclass into a managed and an unmanaged portion. And we differentiate which queries go into the unmanaged versus managed based on the optimizer query cost estimate. So for queries that are less than 150,000 time runs, which is a level we determined across a set of benchmarks, below which queries are relatively short running and relatively lighter weight, we will continue to let those run unmanaged. That ensures that we don't queue them behind heavier work. You still get the fast response time that you expect from those queries. And they tend to be lower memory consumers. Any queries above this cost level, though, we consider heavyweight and sort of say, okay, these are the ones that are going to hurt your system resources if we let too many in the system at a time. So we're going to manage those, and we're only going to let a certain number in at a time, and we're going to queue the rest and make them wait their turn to run. And we pre-compute this, the actual settings here. When you set workload analytics and you create a database, we'll look at the number of cores on your system, we'll configure a specific ratio of sort memory, and we'll set a specific concurrency limit that's meant to balance letting queries get enough resources to run fast while still letting enough in to give you responsiveness. So if you want to understand, if you want to actually monitor the default workload management to see what's going on in your system, a couple of things you can do. The first, we can query that cost setting, which is the boundary for managed or unmanaged queries. So in the syscat.work class attributes table, if you query the work class name sysmanaged queries and the time run cost, you will see the expensive query cost. Here it's the default, 150,000 time runs. You can, if you want to, of course, manually tune those things, so that's why it's useful to be able to query them. Similarly, you can query the default concurrency threshold settings by looking at the sysdefault concurrency threshold. And in this case, what we're showing is that on this database, we will allow 11 queries into the system at a time. The rest will have to queue. As those queries exit, we let new ones in. And in this case, the threshold is enabled. And that's another thing. Again, if you're configuring using the load and go approach, this is all set up by default. But if you came in and you migrated a database and you manually configured it, or you have a mixed row and columnar workload and you set it up without workload analytics, you would need to make sure you turn this default WLM on to be able to manage the impact of the columnar queries on your system. So the other thing I want to point out in terms of the default workload management more relates to query execution. We have several metrics that will help you to assess what's actually going on at runtime because of the WLM. So the first ones would be WLM queue time total and WLM queue assignments total. These are telling you how much time queries actually spent waiting to enter the system. And if you compare that with our coordinator statement execution time, which is really the elapsed time it took to run the query, you get a sense for how much impact queuing is having on your query response times. Likewise, if you query either our mon get activity interface or the simpler mon current SQL view, that'll show you current statements in the system at this point in time. By querying the activity state, that will tell you whether this particular query is queued versus executing. So you can jump on the system and see what queries are in the system right now, how many of them are queued, how long have they been in the system. Gives you a sense for what's going on from a WLM perspective. So that's what I have for you today. Covered a lot of different ground. Hopefully, my hope was that by hitting all these different areas, you'll find some things that are applicable and useful to you, and then you can drill into the examples and use those as an entry point. I will open up for questions now. Scott?
Thank you, David. Very nice presentation. One of your first slides, you mentioned MonGet table has a new metric average columns accessed.
Oh, yes.
What's the tipping point where it becomes unattractive to be a column-based table, right? Average columns access is 1, it's looking pretty sweet for blue. 2, maybe so. 3, maybe so. As the number gets bigger, it becomes increasingly unattractive.
Yeah.
To be in blue. What's your tipping point?
So, I mean, I guess the way I would characterize it, unfortunately, it's not quite as simple as you know, a single tipping point for the table.
You can say it depends.
I do. I will. I hate. Bernie would be proud. I hate to say it, but really, I mean, I would consider that only a sort of a single indicator. I haven't actually looked at, if you're just doing simple scans of the table, where that tipping point would be. Typically, I wouldn't make a decision based just on that metric, because I think it's too narrow. It neglects everything related to the amount of scanning and joining you're doing. Obviously, blue, for example, we could query all the columns in the table, but if what my query is doing is selecting only a very narrow range, where we can do some really good filtering on that initial scan, so that we only actually fetch the full set of columns for a small number of rows, you'd get a lot of benefits out of blue, even though you're selecting all the columns.
Even if you're selecting every column, the encoding compression should be so good that the I/O can be considered better.
Yeah. So unfortunately, I guess what I'm saying is that indicator, while helpful as a pointer on, oh, if it's only 1 out of 100, that's definitely helpful for blue. Seeing 100 out of 100 doesn't necessarily mean the query won't work well for blue.
Okay, let's take that a step further. If that's one of the good indicators, what are 1 or 2 other good indicators? If I were going to look at 3 things to make a decision about a blue table, what are David's top 3 things?
So my top 3 things, what I would actually do is I would actually look at the plan itself. So my top 3 things, I guess, would be the size of data that we're working on. So I mean, if I'm coming in and I'm doing queries on these tiny little tables with thousands of rows, that makes things a little bit more dicey. I tend to look at, rather than looking at the direct metrics, I like to look at the plans and see how many joins, how many groups. So I guess I would say the operator counts. How many joins we have in the plan, how much grouping, and the size of the data. That would kind of be my top several indicators. I know, John, maybe you have I know we do simulations to help figure out, catalog simulations try to figure out which tables will benefit from blue. I don't know the details.
One of the main indications is how much data is going to qualify. So on the extreme end, if it's like point lookup type of queries, single row, unless the predicate is on the unique indexes, they're just support and force primary conclusion constraint. Row stroke can want better in those cases transactional type of queries because they can go right to the data with the single. And so those workloads might not be best for blue. If blue's meant for heavy lifting type of application, you know, and there's a spectrum between OLTP and heavy lifting. But you know, the workloads, you know, more on the point lookup transaction-based side, then probably not easy.
Yeah. So I guess in that case, you kind of.
Result sets favors organized by row. Large result sets favors organized by column. Well, small result sets are lower.
But yeah, but what you said it the other way, you said small result sets for blue. I did. Yeah. So
Small results.
I wouldn't say necessarily it's the results. Yeah, it could be results that that's not necessarily true because you can still have a small result set for blue but it might have done a lot of heavy lifting to find out the results. So it really comes down to how much work did it have to do to find the data. That's kind of,
Yeah.
so if you can find the data quickly with an index, and every access is going to use an index, then roster's probably not. That's your characteristics of different things.
So I guess, I mean, if you have a lot of, where clause, single row, single record lookup,
That's probably getting into...
that hurts a lot more than if you have, a bunch of complex joins and a range where, like where x is greater than.
Not to say that BLU can't handle it in all cases, because it can use the synopsis and skipping in those cases.
Yeah.
It's probably not going to be quite as good as it is.
Yeah, but skipping is not great if I still have to go scan a range to find the one row that I.
I was going to say it's not going to be terrible, but it's not going to be as good as...
Yeah.
Anyway, we're at the top of the hour, so we want to take one more question.
Yeah, I'm happy, and of course I'm happy for you guys to send me. I mean, we had a couple of things I was going to follow up on. I'm happy for you to send me an email if there are things that come up later. Everyone happy for now? Okay, thank you very much.